I'm going to talk today about pyroelectric energy harvesting that beats 10 joule threshold of harvested energy per one thermodynamic cycle. This work has been done in collaboration with many people, as you can see over there. You can, yes, here. I would just precise that the core of the work has been done by our former PhD student, Alvar Torrejo, who is now in Barcelona. Together with Pierre Lheritier, who was our postdoc and now is in CEA in Grenoble in France. And I will also mention our collaborators from Japan, from Murata, Tomoyasu Usui and Sakuyo Hirose, who manufactured all our samples. Okay. Yeah, before starting, I'm just going to tell that I'm from Luxembourg Institute of Science and Technology, the LIST, from Luxembourg, which is a tiny country situated between France, Belgium, and Germany, from who they don't know. And here in this picture that you can see is it's where our lab is located. It's in Bellevaux in southern Luxembourg. You can see these emblematic huge blast furnaces that are remains of an old, steel factory of ArcelorMittal. And that's it. Yeah, LIST has been created in 2015, so it's quite a young organization. And we are about 200 that work in material science. We address different topics: ferric materials, nanopowders, transparent electronics, polymers, electroactive polymers, and composites. So that's for the introduction. Okay, now let's talk about science. The story of pyroelectric energy harvesting in our group started with the electrocaloric effect, actually. So the electrocaloric effect, when you apply electricity to the material that is electrocaloric, basically it either produces or absorbs heat. If you apply it fast enough, you have something like this. So in red, you see temperature. You actually see temperature variation, yes. In red here, you see temperature, and in blue, voltage. So as you go from A to B, you apply voltage, the temperature of the material increases, then the material thermalizes from B to C, while we still apply voltage to the material. From C to D, we withdraw the voltage, the material cools down, and from D to C, it thermalizes again. We had the privilege to work on the world champion electrocaloric material, SCANDIUM tantalate, in the form of multilayer capacitors, which is a really nice form because it's bulky, it provides volume. But at the same time, yeah, you have the picture over there. But at the same time, it has thinner layers because it's a multi-layer structure. So you apply, actually, you achieve higher fields with lower voltages in comparison to bulk. And these samples have been described in these very nice papers. First one coming from the group in Cambridge. It's a paper about the electrocaloric effect in the supercritical regime of the PST that was published in Nature in 2019. And then another paper that came from our lab last year that addresses more the efficiency of these samples. When you look at the electrocaloric properties of these samples, you obtain something like this. So we have delta T due to electrocaloric effects versus temperature. And you have the heating and cooling peak, the heating in red, the cooling in blue. So we see that if we apply something like 16 volts per micron to the sample, we have a temperature change up to 2.3 degrees. That is quite stable in this temperature window from 20 degrees to about 50 degrees. This is really nice. Well, this is nice, but for the practical applications, let's say AC cooling or fridges, this is really not much, 2.3 degrees. So in order to achieve higher temperature variation, temperature span, what we did actually is we put a bunch of these MLCs together and we produced something that we called a regenerator, which is it's a macroscopic prototype. We basically we made these arrays of MLCs that we connected in a way that we will have these channels that allow the fluid to go through the prototype. We put the prototype into a tube, the shrinking tube here that you can see in black, and then we circulated a liquid, a dielectric liquid through this tube in a way. We sort of synchronized the movement of the liquid and the application and the withdrawable field in a way that we accumulated the heat on one side and the cold on the other side of the prototype in something that looks like this. So this is a COMSOL simulation of the experiment. To see that with time, we have red. Yes, so this is the starting moment. And then as the cycle goes, we accumulate the heat on one side and the cold on the other side. And in this graph, I'm showing the temperature of the hot side and cold side after, in time. We were able to achieve 13 degrees of temperature variation, which is still, I think, a world record for electrocaloric prototypes. This has been published 2020 in Science. So after that, our question was, can we do something similar prototype to address now the converse effect? The pyroelectric effect. How good are these MLCs and this material in converting heat into electricity? From the electrocaloric. So if we want to sort of predict or estimate the electrocaloric temperature variation, we use this Maxwell relation, and the part of this equation is the pyroelectric coefficient. So meaning that a good electrocaloric should be a good pyroelectric as well. We also had the question like, how much can we harvest? Can we harvest Joule range energy with our prototype, with our macroscopic prototype? Okay, so with this introduction, I'm going to propose the following points that I will address. First, I'm going to recall the pyroelectric harvesting principle. Then I'm going to talk about material, the scandium tantalate. Then I'm going to give you some sort of information about how to build the prototype. I'm going to show you our harvesting results, and also how efficient are our MLCs and our harvester. I'm also going to compare the efficiency with the Carnot efficiency. And then I conclude. So first, pyroelectric energy harvesting. So in order to harvest energy with pyroelectric effect, we need temperature variation in time. So I'm just to make a difference. Thermoelectric harvesting needs temperature gradient. Now we need temperature variation in time. So it's two different things. Temperature variation in time implies thermodynamic cycles. And actually, that's what we use for harvesting. We use two cycles, Olsen cycle, which is similar to Ericsson cycle, and the Stirling cycle. Olsen cycle implies two isothermal branches and two isofield branches, whereas Stirling cycle implies two isothermal and two isocharged. So it's a bit complicated to imagine. So that's why I put here a PE loop. It's quite simple. It's simpler to explain it with PE loops. So here I'm plotting two unipolar PE loops at two different temperatures of PST. The blue one is 20 degrees and the orange one at 90 degrees. And let's start with the Olsen cycle. So we have first isothermal charge. From A to B, what we do is we charge our capacitor. That's it. Simple as that. From B to C, we try to be isofield, so we keep the same field on our material while we heat our sample. From C to D, we just discharge the capacitor at 90 degrees, and then we cool down. The Stirling cycle is a bit different because we have the isocharge branch. So we go from A to B dash where we charge from at room temperature, at our initial temperature. Then we disconnect the sample because we are in isocharge regime from B dash to C. We go from B dash to C. We heat. Actually, what we see is when we monitor voltage is that voltage increases spectacularly. So we can charge it something like 10 degrees, and then the voltage increases to 400 volts. It's quite incredible to see. And then from C to D, we discharge at high temperature, and then from D to A, basically we just cool down. Interesting thing about this graph is that we can actually predict what is the energy density that we will harvest from this equation, electric field over integration over the electric displacement. Actually, when we charge for let's say Olsen cycle, we go from A to B, and the blue part here is the energy that we put in the material as we charge it. Then we heat our MLC, and then we discharge. We actually recover the blue and the orange part. So the net energy that is harvested is the orange part. For Stirling cycle, we have something similar, but we end at the gray bar. So we put in the energy that is in blue, this triangle, and we harvest the net energy that is harvested is the orange one. Okay, now let's talk a bit about scandium tantalate. It's a typical perovskite structure. You have on the B side scandium or tantalum. If the 1-1-1 planes of scandium and tantalum alternate in space, you have order that's equal to 1. It's really interesting for us. I'm now to later on the B side. If we don't have any order, so if scandium and tantalum are distributed randomly in space in 3D in our crystals, the order is 0. In practice, we have order that is in between 0 and 1. If we have order that is equal to 1, we have very sharp phase transition that is around 20 degrees. And this gives rise to very good electrocaloric properties. We have larger temperature changes at around the phase transition. The samples that we work with have order between 0.8 and 1. It's a very good quality. All right, so let's try to harvest energy from 1 MLC. The experimental setup looks like this. So you put 1 MLC under the infrared camera. We put it on a stage that is a link-up stage in order to control the temperature of the sample. And we have it, of course, connected to a Keithley in order to apply voltage and also to monitor voltage and current. And we perform Olsen cycle. And we got something like this. So on top you have in blue, in red you have current, in black you have voltage. In yellow, you have temperature variation, and in green, energy at different states of over time. So first, we charge our material, normal from A to B. We have a non-zero current, and we charge it to 600 volts, so we achieve 600 volts, basically. Then what we do is that we start heating while we try to maintain the same field in our material. Interestingly, what we see is a negative current that comes from the sample, which actually means that we start harvesting energy. And we have it here we see here that the green curve initially that is positive because you gave energy to our sample, is decreasing as we increase temperature. Then we arrive to a plateau of temperature where we don't harvest anything anymore because we are in equilibrium state. And then from C to D, we discharge our capacitor. So we go back to 0 in voltage, and we have a negative peak of current. And then that's about it. So this experiment enabled us to see that with 1 MLC, we can harvest something like 60 millijoules of energy. Okay, now we want to go further and to build an actual prototype. Okay. An actual prototype with our MLCs. So I'll just go very, very fast through these. So we have our material, our brick. Then we have we need a temperature oscillation. We have two baths, a cold and a warm one, of silicon oil in order to change temperatures. And then we have our heat transfer done with this structure. So we again put our MLCs in a prototype in this structure in order to help the heat transfer to go through. Okay, this is our experimental setup. And then this is what we achieved with the smaller prototype. We see that basically higher we go, higher we initially charge, and higher is the temperature span, more we can obtain. So we are, with our first results, we could already get something like 3 joules of harvested energy, which was quite good. Now I'm going to show you our best results that look like this. So in a picture in here, you can see actually 8 prototypes. They are connected in parallel, connected in 2 loops in cold and warm reservoirs of silicon oil. There is a peristaltic pump, and that allows the liquid to flow through, and the Keithley and thermocouples that monitor everything. And what we got actually is that if we pay 2 joules of energy initially, we can get net energy of 11 joules at the end. So this result has been published last year in Nature. And basically, this is the best value since the 80s, since the publication of Olsen, who harvested 6 joules with Tindo PZT. And then, yes, I want to show you some, the efficiency part. Of our MLCs, and also the current efficiency. I'm just keeping to the actual results. So we have efficiencies that are 0.4%. It's not, it's not too bad, but it's not, in comparison to solar panels, we are very low still. What is interesting though is the efficiency in comparison to Carnot efficiency, where we can actually obtain larger values, twice as much as the best value until now, which was done in the lab of Lane Martin and published about 4 years ago. And that's it. So just to summarize, we are able to harvest 11 joules, which is really nice because it's a real energy that we can use afterwards. And this is because we have these nice material, PST MLCs, that were sort of put together in this macroscopic prototype that works so nice. And then in the next future, we'll address power and the overall efficiency of our device. And with this, I would like to thank you for your attention and take any questions.
Thank you. So this is Karen from Rutgers. So I just, was wondering in terms of materials challenges. So do you, the PST material, is there an opportunity there for increased performance?
Yeah.
Materials design or all the other other aspects of the
Actually, yes. Yeah, that's a very, very good question, because a way how to increase efficiency of our device would be to actually go and explore this. So we see that, that we are efficient at the transition temperature with temperature span is quite low. So the way how to increase the overall efficiency of the device would be to have materials that will have transitions at different temperatures, most probably, and we would like to take advantage of this cascaded system or a gradient. So yeah, so we definitely want to address and are addressing materials, or we are trying to engineer the transitions in PST.
Okay, great answer, thank you.
Okay, another question? Yeah, what about the cycle? Presented at the beginning, 2 different cycles, remember?
Yes.
So why did you look at the Olsen one, and it would be interesting to investigate?
Yes, the Olsen is actually the cycle that gives us the maximum energy. it has been, I mean, demonstrated even, by Lane Martin, who also addressed this, that Olsen cycle actually give, because it gives us the possibility to get the whole, to actually harvest more. The Stirling cycle is simpler because we give less at the beginning, and it's more spectacular because, I mean, we actually see when we monitor the voltage on our sample that we give in only 10 volts, and then the voltage just amplifies like crazy at the end. It's because we go from here in field to something to here. So we see in real time the voltage increases. So actually we started with Stirling because it was more sort of intuitive, and then we went to Olsen because this one is more, gives the opportunity to harvest more quantitatively.
Thank you. Okay, so let's thank you again.
Thank you.
The next presentation will be given by Veronika from University of South Florida. Who's going to talk about the effect of medicine on the electrical effect in various mechanisms.